independent from the first part. So you can forget about the Baratical surprise. You have to give some kind of of motivation. So the only thing that you have to keep in mind for the second part is the little disk picture. Okay, forget also about cubes. Only disks exist now in this room. Okay, and so actually in this second part I would like to address so I said that an operad is En if it is connected to the little n disk by a chain of equivalences of operads. In the second part I would like to count how many equivalences I have. And the answer is provided by this, by the Grothendieck-Teichmüller group. Okay. So first a reminder, so an operad is a class of operads which is defined by a reference model, so the operad of little n disk. And the goal of this talk is to prove the following statement. The Grothendieck-Teichmüller group is the group of homotopy automorphisms of E2 operads or of rationals. We have several things to explain. So probably I will give another definition of the Grothendieck-Teichmüller group, okay, which is equivalent to the previous definitions.
We know what question to ask.
Yeah, and I will have to explain what is a homotopy automorphism of operads. So E2 operads, now it's okay, but I will re-explain what E2 operads are. I'll give another some kind of characterization of E2 operads, and to explain this sense of this expression over the rationals. Okay, so this means that I have to take some kind of rational completion at something. So there is another statement, so maybe I will explain that next week, the relationship with Untitled associators. Okay, so the plan of this...
What was the statement?
Yeah, so it's about the torsor Untitled associators and homotopy classes of rational formality quasi-iso. Okay, so the plan is the following. So I will go back to the little disk picture. I would like to explain, so the first part I would like to give some kind of recognition criterion for E2 operad, which is specific to E2 operad case, so E2 operad case. And this recognition criterion is given in terms of fundamental groupoid of this operad. Okay. And I would like to explain that the fundamental groupoid of a little 2-disk operad is actually an operad governing Brownian monoidal structure. And I'm going to explain the notion of a homotopy automorphism in the second part of my talk, and I will tackle applications to Grothendieck-Teichmüller group, or rather around, it's applications of Grothendieck-Teichmüller groups to the homotopy of E2 operads in the last part. Okay, so first fundamental groupoids. So just remember, so this was explained in previous talks during this semester. So if you take the space of little 2 disk, of little 2 disk in a big unit disk, so I've explained during the first part that this space is homotopy equivalent to the configuration space of points in the open unit disk. Okay, and the homotopy of this space is known, so it's just if you take the homotopy group of this space, this is the pure braid group if the degree is 1, and this is the trivial group otherwise. Okay, so where PRs. So this means that this space, in these conditions, completely characterize this space. Any space which has these homotopy groups is homotopy equivalent to the configuration space. So topologists say that this space is a KPR1 space, an Allenberg-MacLane space of type KPR1. So 1 refers to the degree here. Okay, and this PR, so it can be given as, so this identity can be given as the definition of PR. This PR is the pure braid group on R strands. So the idea is to elaborate on this connection in order to characterize the operad D2 from structures at the level on PR. But so I don't see how you could define a symmetric structure on PR. And you have difficulties with base point if you deal with fundamental groups. And the idea is to use fundamental groupoids instead of fundamental groups. And in this first part of the second lecture today, I would like to explain that this fundamental groupoid pi of D2 is an operad in groupoids, and you can use it to retrieve a combinatorial model of D2. Okay, okay. So let's start with fundamental groupoid. Okay, so pi of D2, pi of x. So pi of x is my notation for the fundamental groupoid of the space X.
Can I ask, do we have units or not? So can R be 0?
Yeah. That's, yeah. I will explain this unit points later on. So for a moment, I draw the unit. Okay. I will implement units in the second step. Okay. So this is a groupoid. The objects of this groupoid is the set D2R underlying the space D2R. Okay. And the morphisms from one element in D2R to another one are homotopy classes of paths going from this A bar to B bar. Okay, so it's the usual picture. And in the little 2D space, so this equivalence between D2R and the configuration space implies that you have a bijection between the homotopy classes of paths D2R and homotopy classes of paths in the configuration space. Okay, and this bijection implies that the morphism sets of this morphism sets are identified. So you can identify this object. It's not exactly PR, but you can identify it with the coset of PR inside the whole Braille group. Okay, so I'm going to give a picture of a morphism in this fundamental groupoid. So it's the domain. Okay, you start with such a configuration of little 2 disk. Okay, the codomain is this configuration, and between you have a path in the configuration space, which in the up to homotopy, this is the same as a path in the little 2 disk space going from this configuration to this one. Okay, so this is the domain, the codomain, and this is a picture of a morphism from A to B. Okay, so the basic idea you have at least to retain the little disk picture for the objects, but for morphism you can go down to configuration of points. Okay, so. And I claim that this fundamental groupoids form an operad. I mean, so first, you have an obvious symmetric structure on the fundamental groupoid. This means that each permutation, S, next sigma R, gives rise to a functor from pi of D2R to pi of D2R. Is a functor. So it's a map at the object set level. It's a map at the object set level, and it also carries morphisms in D2R, in the fundamental groupoid, to morphisms coherently in the tangent. Okay? And you have also operatic composition products. So this operatic composition products are again functors between groupoids. Okay, maybe, and so as a consequence, the collection of fundamental groupoids of a little 2 disk operad form an operad in the category of groupoids. So maybe I'll give a picture for such a composition. So you see, so it's so this is the domain again. So I'm looking at the composition of 2 morphisms. I would like to compose this morphism on the first position of this morphism here. First at the object level on the domain. So I'm dealing with a periodic composition of a little 2D. So this means that I plug this little 2D configuration in the first little disk of this configuration. So I get this picture. Okay, so if you remember, maybe I can mark okay, plug this little disk here. Okay, I do the same thing for the codomain. Okay, so I get this composite configuration of little disk, and so if you look at the if you regard this morphism as a homotopy class of paths, you imagine, so in the little 2D space, you imagine that the composite of this path inside, you compose this path here, this path of little 2 disk, and you get this kind of cabling operation. Okay, you just insert this configuration into a path of little disk going from here to here. Okay? So that way you fix every problem with fundamental groups, so you get an operad in the category of group ways. Okay? So some ideas. One point. Say, okay. So I took D2R as object set, but there is no need to take the whole space D2R. It's just sufficient to take a subset which is preserved by the operatic composition structure. And so the space is connected. So it's okay. So if you take a subspace X, if X is connected, then you can look at the restriction of a fundamental groupoid pi of X to this subset S, and you get a groupoid with this object set which is equivalent to pi X. So it's just the full. So just the full subgroupoid generated by X, S. So this map is not an ISO, it's a groupoid equivalence. It's a groupoid equivalence. So it's a bijection on morphism sets, and it's a bijection between isomorphism classes of objects. Okay? So, and to keep, so I will take such restriction for the fundamental groupoids of little 2D spaces, and to keep the operatic structures, I just need to consider a collection of subsets of this form which are preserved by the operatic composition operations. Okay. And
but the only condition on the set S, individually, you said it's connected.
Yeah, if X is connected, then you can take any S.
In this case.
Yeah. No, the S has not to be connected itself. X. So
X is connected.
You need at least what you need in general is to assume that you have an object. Each connected component of X intersects S. Each path connected component of X intersects S. Okay, but S is discrete, so it's just. So in the example, this S will be really a countable set. So it's okay, and this is my way to define also what I call, following Emmanuel Barnatan, the groupoid of parenthesized bright. So at least, actually, it's slightly different from the categories of parenthesized brights considered by Barnatan. I will explain the difference later on. So in Barnatan's picture, so Barnatan is dealing with categories and some kind of formalism which is related to the formalism of universal algebra. And I'm dealing with operads.
Are you going to tell us what you mean by parenthesized bright?
Yeah, exactly. So I'm going to, maybe that's better if I explain. So I should say, so I will define this parenthesized bright operads as such a suboperad of a fundamental groupoid of little 2 disk. Okay, you will see the picture. So it's given by such restriction of fundamental groupoids to certain object subsets. Okay. And so what I need is that these object sets are preserved by the operatic composition structures. Okay, to get that this collection of full subgroup weights of pi of D2R forms the suboperad of D2, of pi of D2. Okay, so I'm going to give a picture. So actually, I'll use a bit more than just preserved by the operatic composition structure. You will see. So the objects, so the best first is to give the picture of a configuration that I'm considering. I'm considering configurations of this form. So this one is linearity 2, this linearity 3, and linearity 4. I have such configurations. So the condition is that the little disk of configurations are centered on the horizontal axis, and the little disk form a dyadic partition of the horizontal axis. Okay? A dyadic partition. Dyadic, yeah. Okay? So.
That means the radius is 2 power of r.
Yeah, exactly.
R.
Yeah, exactly. Something like that. Yeah. Okay. And so.
You don't mind which order you put them in, do you?
Sorry?
I mean, would you allow a disk of radius a quarter, a disk of radius a half, followed by a disk of radius a quarter?
Yeah.
Okay.
Yeah. In fact, so formally what I'm considering is the suboperad of D2 generated by this configuration. So it's you get exactly the kind of picture. Okay? And okay?
Okay, great.
Yeah. So omega is the suboperad generated by this little disk configuration. And the statement that this operad is identified with the magma operad, this means that this operad is free. Okay? So this means that maybe I will draw the pictures. Okay. You can identify, so it's the operad which is freely generated by this element. Okay? So this means that each omega R has the same thing as the set of planar binary trees. With R inputs. Okay, so for instance, maybe I'll draw this configuration here.
But isn't it, sorry, I don't understand this proposition, because aren't you saying it is? It's equal to?
Yeah, is equal. Is equal if you like. Is isomorphic.
You just said it's generated by that one element.
Yeah, I'm considering the operad generated by one element, and my claim is that it is freely generated by this element.
I see.
There is no relation.
Gotcha. Yeah.
Okay, so
generated in the suboperad.
Yeah.
I understand.
yeah.
It might share
Okay.
rotation.
Okay, so maybe I can draw the trees. So this is this. So you take here the one binary tree with the single binary tree with two inputs. And here you get this tree, here this one, and here this one. So in general, it's very easy to retrieve a tree from such a dyadic decomposition. For instance, if I take this decomposition, okay. So first I split the disk in two parts. So you see I get a fork at the bottom, and so I look at this dyadic partition of half of the interval to get and then again I can split this picture in two parts. Here so here the process terminates, and here I can continue in steps, and here I get only one fork. Okay. So this gives the correspondence. So it's free as a suboperad, as an operad without units. I'll add units later on, actually. Okay, so Okay, and so I'm considering, so I'm taking PAB, so PAB is pi of D2, the restriction of pi of D2 to this suboprad, omega, okay, which is a suboprad of D2. So this means that the objects are little disk configurations of this form, and the morphisms are paths in the configuration spaces going from the center of such a configuration to another one. Okay, so here are examples of morphisms in PAB. So you have this one, which is actually an associator. So you see you have this operation, mu, which it's an object. So you can regard this operation, this object, as a kind of multiplication if in the object set of PAB. And this multiplication is not associative, but you have an iso in PAB going from one configuration to another one. Okay, so there is a morphism there is a path in D2, making this composite isomorphic to this one. Okay, so maybe, and you have another morphism which is the braiding. Okay, so which goes from mu to mu transposite. Okay, and in some sense, so the operad PAB, so at the object level it's a free operad, and so at the morphism level it's generated by these morphisms. And you have also generating relations with the morphism, which are the next picture gives the pentagon relation. Okay, so you see I'm starting with this. Maybe I'll draw the trees. So I'm starting with this composite. Okay, one. Okay, then I have two, and the last configuration is this. Oops. Okay. Okay, and you can combine associativity iso to go from this configuration to this one. So for instance, I think that this morphism here is you plug, so you just plug you just plug the associativity iso on this tube. Okay, so you get the multiplication or mu, sorry. Mu, alpha, and the identity. Okay. So here it's alpha of the identity, mu, and the identity. Okay, and so on. So you have a threefold categorical composite, categorical composite of morphisms which are made of operatic composite of identities, so the identity of mu, of the object mu, and of the associativity iso. And you have a similar composite on the other side. And if you forget about the composition process, the categorical composition process, you see that this braid here is exactly the same as this one. Okay? So that's why you get an identity at the morphism set of a fundamental group weight of pi of D2. Okay? So the next relation are the hexagon relations. So you have this one, okay? So which is one way to write the hexagon relation. So you can write down explicitly the composite involved maybe. So here I'm taking the multiplication of C and the identity. So no, maybe the braiding was written tau. And here this is the associativity, and here this is mu of the identity and tau. So I get this composite here, and here I get two associators, tau of mu and the identity, and alpha. Okay? So this is one hexagon relation, and the second hexagon reads as follows. Okay? So what I claim, so it's a kind of combination of Maclane's coherence theorem, of Andreas' strict definition of three braided monoidal categories. So it's an operatic version of these theorems. Okay, first point, so I'm looking at operad morphism phi from PAB to P. So maybe I can consider, so yeah, P is any operad in this statement. I can assume that P is the endomorphism operad of some category. Okay. For instance, you can take the endomorphism operad of some category C. Okay, so this is that P are the objects. So it's an operad in the category of categories. The objects are functors from C cross R to C. And the morphisms are natural transformations. So, and I would like to describe the morphism from PAB to P. Okay, so for instance, for this kind of P. Okay, so first determined by giving an object M in the object of P2. Okay, in 2. So in this case, M should be a tensor product operation. Multiplication on C. Okay, so it's on C2. Okay. So this M represents the image of this mu, the little disk configuration mu. Here, draw the picture. Yeah, maybe. So in the object of PAB, you have this configuration, mu, which has to be mapped to some M on C2. So it's a bifunctor from C plus 2 to C. Okay. So you also have to give the image of the associator, alpha. Okay, so alpha is an iso in PAB3 from this composite of mu to this one. And this iso has to be mapped to some A. Okay, this is alpha. Has to be mapped to some iso from the image of this composite of little disks. So this is just x1 tensor x2 tensor x3. This composite is mapped to x1 tensor x2 x3. And alpha has to be mapped to an iso A connected base composites of the multiplication operation. Okay? And similarly, the braiding tau has to be mapped to braiding in C for this tensor product operation. Okay? And so the operad morphism is determined by this data. And to have a well-defined operad morphism, you have to assume that A and C satisfy the pentagon and hexagon relations in P. So in this example, in this endomorphism operad, so it's okay. So in C.
Actually, this is true for any operad.
Yeah,
Not
P is
just in
any.
the category of categories.
What do you mean?
No, you need the isomorphism, so you need to have not only objects but also morphisms. So P should be operating category.
So P and PAB have to live in the same world. So it's
Okay, you need to have morphisms.
so phi is supposed to be a morphism of operads in the category of categories. So this object is an operad in the category of groupoids, which I can forget about the groupoid condition. So it's okay. So in this case, okay, it's or I can take the
So
subgroupoid.
algebras are exactly braided categories.
Exactly. So we say that algebras about PAB are exactly braided monoidal categories. Okay, and with with general associativity isos. Okay, there is another operad which I denote by COB, which is the chord braid operad, which governs strict braided monoidal categories. Okay, and the objects operad the object sets of this operad are identified with the components of the associative operad. Okay, in some sense. So this operad PAB can be obtained by some kind of pullback process from COB by replacing this as by the magma operad. Okay. So.
Or some identification.
Yeah. Okay. So I need to. Okay. Yeah. So it's PAB is the operad governing braid monoidal categories, but for a moment without units. Okay. So actually, I need to consider strict units. I mean, so that's why I'm adding units in the second step. So this operad, so to add units, I just add this term, this RT0 term to the operad PAB. Okay, and then there is I just specify the additional operad decomposition operation this term by some kind of restriction structure. So for this, the fundamental groupoid picture doesn't really work. So I mean, in the little groupoid picture, in the little disk picture, you have a removal operation. I mean, if you take this little disk configuration, if you compose with a unit at the second place, the second position. Okay, so the unit in this case is just the empty configuration of little disk. Okay, then you get this kind of picture. So you see this operad omega is not preserved by the composition with this RT0 operation. So what I can do actually is to replace this configuration of little disk by the identical one by a canonical path in the fundamental groupoid of D2. So in some sense you can rectify the units in the fundamental groupoids to get this operad, which I denote by PAB plus, where you have a unique element in RT0. Okay, the same object sets in RT larger than 0, and and you can extend the statement. So it's an operad that governs braided monoidal categories with strict units. Means that if you take x1 tensor E, you get exactly x1, not an object isomorphic to x1. Okay. So it's at some point I need to rigidify the process. And to rigidify the process, I implement artificially strict units in my operas. Okay, so yeah, this statement, which is it can be deduced from Fedorovich recognition criterion. So I'm going to give another proof. Okay, I claim that this operad, so it's B stands for the classifying space. Okay, so B. So for a group BG, it's just this space such that, which is G in degree 1. Which is trivial in degree different from 1. Okay? Okay, so the classifying space of a group G. So this is for a group. You can extend this space this classifying space construction to groupoids. And you can check that this construction is good, it's monoidal, so that it carries operads in the category of groupoids to operads in simplicial sets. Okay? So I form this classifying space operad associated to the parenthesized braid operads. And Fyodorovic's theorem implies that this operad is E2. Okay? Maybe I have not the proof of my slides. Yeah. It's actually very easy. So I've established. So I've established that pi of D2. So it's equivalent as an operad in groupoids to this full suboperad generated by omega. Okay. So let's forget about your units. Okay. So this is PAB. So this is an equivalence of operads in groupoids RET-wise. Equivalence of groupoids. Each RET. Now take the classifying space of this operator in groupoids. Okay, you get your P. And because it is an occurrence of groupoids RET-wise, you get a chain of automorphisms which are weak equivalences of topological spaces at the classifying space level. Okay, equivalences of categories induces homotopy equivalences at the classifying space level. Okay, so and now it's a so there is an adjunction between fundamental groupoid and classifying spaces. So at least it's true at the simplicial set level. But anyway, you can deduce from this, and because this object consists of K of Allenberg-MacLane spaces, you can immediately obtain that this operad in space is equivalent to D2. Okay. So it's okay. So and this gives a very quiet equivalence. Okay. So it's another proof. So because in Fyodorovich method, so Fyodorovich is taking the universal covering of B PAB and check that it is contractile. So it's equivalent. So it uses some kind of different operad structure. So it's here you can just use the adjunction between fundamental groupoids and classifying spaces. Check that it is monoidal to get the result. Okay. So
what did you with the plus?
Yeah, you can add the plus.
Yeah. But at the level of spaces?
Just at some point in RET 0, so you can put the plus where you like. So
It'll give you a base point at D2, won't it?
Yeah, does it give you just a base
no.
point or something?
The plus is just adding something in RET 0.
Oh, yeah.
Gives you something floating.
So without the plus, without the plus, you have empty set in RET 0,
Yeah.
and the plus is just added something,
It's at a point.
a point in RET 0, no more. Okay. Yeah, maybe you don't need plus here. No conversion. Okay. Okay. So now we have a nice model of E2 operad. So it's, and you see you can extend this theorem. Each time you have an operad in spaces, you compute the fundamental groupoid. Check that this operad consists of Allenberg-MacLane spaces. Compute the fundamental groupoid of this operad. If you get something which is equivalent, which is RET-wise equivalent to PAB or to curl braid operad, then you can conclude that it is E2. Okay. So since you can compute, so the trick is with that you deal with fundamental groupoids rather than fundamental groups. So you see, so it's not so So you have some difficulties. You have to construct equivalencies rather than isos. So you have only done half of the way actually with this statement. Okay. So anyway, you have this combinatorial model of E2, and I'm going to work with this model. So, okay. So now I would like to explain.
That model is just a blow up of my spineless cacti model. I mean, basically, it's homotopy equivalent to spineless cacti.
So?
That model is homotopy equivalent to spineless cacti.
Mm-hmm. Spineless?
Cacti.
Yeah.
You mean
Which is my favorite version.
Yes. Yeah. Yeah.
Yes.
So you have also a variance of you have many instances of braided of E2 operads. So it's because you have such a simple criterion to recognize E2 operads. That's the point. Okay. And I would like to state this corollary. If you take the classifying space of a braided model category, then you can deduce from the recognition theorem from this statement and the recognition theorem of iterative loop spaces, but this is equivalent to a double loop space.
Is that in Fyodorovic's paper?
Yeah, I think this is Fyodorovic's statement
Yeah,
actually.
yeah.
This is
Yeah, no, sorry, just checking.
Okay. So basically, I stated the general Boltzmann-Vogt and Mayer recognition theorems, but in practice we are only able to recognize one-fold loop spaces, double-fold loop spaces, and infinite loop spaces. I don't think there is any example in nature where something is a four-fold loop space, except the universal examples. There are some examples where we don't know if it is n for every n, but it's not. Yeah. So I mean, if you find an example of a space which is a four-fold loop space, but not a five-fold loop space in the nature, then tell me. Yeah, no, except the universal.
There is an example. You asked me. But there is an example, isn't there? I mean,
Very interesting.
never mind. I mean, Ulrich Tillman could have an example. Or something which was a two-fold loop space, but proved not to be a three-fold loop space.
Yeah, but as I said, so the only example is nature are one-fold loop spaces, two-fold loop spaces,
Oh, I'm sorry.
or infinite loop spaces. What I would like to see is an example of a three-fold or of a four-fold loop space in nature.
I misheard you. No,
Basically,
I was
so
rising
this
to
is-
the challenge, wasn't I?
Yeah, basically you have good categorical machines to recognize one-fold loop spaces, two-fold loop spaces, and infinite loop spaces. So you have a version of this corollary so in the E1 case it says that the classifying space of a monodal category is a one-fold loop space, and so this is the statement for the E2 case. In the infinity case, it states that the classifying space of a symmetric monodal category is an infinite loop spaces. Okay. So there are some generalizations, but yeah. So it's more difficult to recognize the intermediate loop spaces. Maybe one reason is that if you look at En, you have Sn-1, which is a quite the n-1 dimensional sphere, which is a quite complete space from the homotopical viewpoint. Okay, so let's start with homotopy automorphisms. Okay, so I would like to recall the definition of a recurrence of operads. So I've said that an operads phi from P to Q is a recurrence of operads in topological spaces if the components of these morphisms are recurrences of spaces, of topological spaces. Okay, and I'm using this notation to mark the class of recurrences. So what I would like to do is to define a homotopy category of operads. And the natural way to do that is to say, well, the homotopy category of topological operads is the category obtained by formally inverting the this recurrences. Okay, so from this definition, it's not clear that it is a category, because, especially in the topological case, because so you are dealing with zigzags, and the zigzag might not form a set. So the main point. So, okay. Anyway, let's continue. And I can define.
Reality comes from the model categories.
Yeah, exactly.
Yeah.
At least
So, but we don't.
the set theoretic issues can be worked out.
Yeah, but just to say one more.
Yeah. Okay. Then you have also homotopy automorphism groups. So what I call the group of homotopy automorphism, it's just the groups of for an operator in topological space. The group of homotopy automorphisms of P is just the group of automorphisms of this object in the homotopy category. Okay. So from that definition, it's completely impossible to compute this group. Okay. So it's even to prove that it's a well-defined set. So that's why I need another definition. Okay. But you see, this is the kind of things that we deal with. So at some point we deal with chains. Okay, so this means that any such chain gives rise to an element in this group, represent an element. So to address to compute such groups, you need some extra structures, and model category is one way to do that. Okay, we'll give a theorem. So vacator of operads in topological spaces. So I'm not going to explain every concept. It's a coherently generated model category. Okay. This means that you have a class of recurrences, which I've already defined, and a class of fibrations. And these classes are inherited from the ambient category of topological spaces. So I've already defined the recurrences. And the fibrations are the automorphisms, which are self-fibrations of topological spaces, RET-wise. Okay? So this is the kind of distinguished class of maps that you need to do computations in topology. And you need another class of objects, which are the coherent objects. So in the case of topological spaces, you consider the cell complexes, which are good realizations of the coherent objects. And in the case of operads, you can also define a class of coherent objects. So basically, they are just characterized by some good homotopy lifting property. So acyclic fibrations, to recall what it means, acyclic fibration. The class of acyclic fibrations is the class of morphisms which are both recurrences and fibrations. So I'm not going to explain this statement. I just want to say that this enables you to do computations, so that it's setting this as a corollary. What you are doing, so you use this kind of structure to compute morphism sets in the homotopy category of topological operads. And to do that, you don't deal with the objects themselves, but with resolutions of these objects. So formally, from this theorem, you can deduce that every operad P has a coherent resolution. So coherent object in the model category means that the initial morphism is a cofibration.
Suppose you know the theorem without the word operad, what you need to do? I mean, what you need to do in that theorem, which is well known, in order to add the word operad.
You're putting it back.
The topological space?
Yeah, I suppose you know the thing.
So first, in the case of topological
I
spaces,
just want to add
has
word
the
operad.
same model structure.
Yes,
as the
but what do you need to check?
What do you need to check? So okay.
Do you need to check?
So
What do you need to check?
you need, you have.
You need to check it.
Yeah.
No, but I mean, no. I
So,
mean, just to add the word operad.
the main
What
point-
is the...
Yeah. So what you need to check
The main problems is with push-out axioms.
Yeah.
Push-outs in cofibration operads are quite different from push-outs under, and to check
Yeah,
whether
that this
these
is
axioms
compatible with the operad structure in a way.
Yeah, but that's to go from topological spaces to operads.
That's what I'm interested in.
Okay. Okay.
There's a general theorem, isn't there?
Yeah.
To more like Berger.
Yeah.
No, we do not.
Which one?
The transfer from topological
No,
spaces to topological
No, the
operads.
method of Berger-Mordijk doesn't work in the topological context.
Oh, doesn't it? Oh, God.
You need some, yes,
Just from spaces to operad.
yeah. So you have the same model structure in the category of topological spaces, and the cofibrations. So you have good model for cofibrations, which are the relative cell extensions. Yeah. And you. So but in the operad case, cofibrations mean so it's you need some kind of operatic analog of the cell extensions of topology. And the operatic analog has some kind of attachments, of free attachments. You attach along morphisms of free operads, free operad morphisms. And you have to check that this morphism behaves well with respect to this kind of thing that you do when you do homotopy computations. Okay, that's the main point. So you want to check that the push out of that's what the crucial point is this. You have to check that the push out of an acyclic cofibration returns a weak occurrence.
So it's all hidden in. There's a lot packed into that second point, isn't it? The co-vibrations are characterized by.
Yeah.
There's a lot packed into that.
Yeah,
second
exactly.
point.
Yeah. You have to.
You have to prove.
You need a more effective characterization.
You have to prove that the things characterized by that left
Yeah.
property with respect to acyclic vibrations satisfy the axioms for
Yeah.
co-vibrations.
Why do you see that Berger-Mordijk method doesn't work for topology?
Because they require some strong version of a small object argument.
With
Right.
the option,
Which-
they have it, no?
They require that the domain of generating cofibration are small with respect to all composites of morphisms in the category. And here the domains are spheres or which are small with respect to composites of topological inclusions. So you have to analyze some push-outs to check that you get topological inclusion, things like that. So this makes the category of topological spaces more complicated than the category of simplicial sets. For instance, in the category of simplicial sets, Berger-Mordijk argument works perfectly well. In the context of topological spaces, this is not sufficient. You need some analysis of push-out.
I see. Okay. That's good.
Okay. Okay. So you have this structure. What I claim that so you have this notion. The main points that together with the notion of a cofibrant generated model category, you have the notion of a good resolution, what I call cofibrant resolutions, and authors say cofibrant replacement. And basically, the idea is that you can compute morphism sets by using such resolutions. So that's the same kind of thing that we are doing in classical homological algebra. To compute morphism sets in the derived category, you take a resolution of a source and maybe a resolution of a target, but in that case, not necessary. Okay? So, I mean explicitly, the morphisms of operads from P to Q in the homotopy category are homotopy classes of maps, of operad maps, for R to Q. So, here you have no chain, just maps going, just operad morphism going from R to Q, and you divide this morphism set by a suitable operatic homotopy relation. Okay, so to compute this set, you have to do two things. First, to construct a cofibrant replacement to have an explicit, or at least a manageable cofibrant resolution R of P, and to compute homotopy classes of maps defined on this cofibrant replacement. Okay? So I can define very easily this operatic homotopy relation. Okay? So I start with polymorphisms of topological operads, phi and psi from P to Q. And I say that these morphisms are homotopic as operad morphisms. If I can go from phi to psi by a continuous path of operad morphisms. So each phi t is supposed to be an operad morphism from P to Q, and the the family of this phi are supposed to form a continuous family. So to define properly the notion of a continuous family, yeah, maybe it's okay because you can embed.
T cross I, is it?
Yeah, you have to.
Yeah, that's
exactly,
fine.
exactly.
Couldn't you do everything
Exactly.
superficially?
Yeah,
I mean,
you can do everything
from the
simply.
start.
Exactly.
No, but everything could be superficial.
Yeah. Continuous family means the extension.
Yeah.
This extension is continuous, which this creates some problem in the case of topological spaces, which I'm not going to address. You have also problem with adjunction, with mapping sets.
Why can't you do everything in superficial sets?
You can do everything in
You could
simple.
do everything in superficial sets.
Yeah,
From the start.
yeah, from the start. But there is another point. In simple sets, so not all objects are cofibrants. This means that you have also to perform, not all objects are fibrants. So this means that you have also to perform a fibrant replacement on the right-hand side. Okay? Actually, to do computation, I'm working with simple sets, not with.
Yeah.
But things are easier to understand in the topological context. Okay. Okay. And so I have this notion. I can also define the notion of a homotopy equivalence of operads. So morphism, an operad morphism is a homotopy equivalence if it is invertible up to homotopy. And this means that you have a morphism in the converse direction, such that psi is homotopic to the identity as an operad morphism, and conversely, psi is homotopic to the identity as an operad morphism. So I will use this notation for homotopy equivalences. So you see, this is for weak equivalences, homotopy equivalences, and I will use this notation for isomorphisms. Okay, yeah. Such. Okay. Okay. And the one point. So you know, if you work in topological spaces, every map between cell complexes, between CW complexes, which is a weak equivalence, is automatically a homotopy equivalence. It has an inverse up to homotopy. And the same is true in the case of topological operads, provided that you deal with weak equivalences between cofibrant operads. You have to deal with the notion of a cofibrant object in the case of topological operads. Okay? Oops. Okay, so this implies that if you want to compute, so I will summarize the concept. So if I want to compute the set of homotopy automorphisms of an operad P, I have first to pick a cofirmant resolution R of P, and this set of homotopy automorphism can be identified with a set of homotopy classes. So, homotopy classes with respect to the homotopy, to the aperiodic homotopy relation of self-homotopy equivalences of R. Okay. Okay. And you can check that, so for instance, you can check that this object is a homotopy invariant of R. Okay. I should say it's a homotopy invariant of R as a group. Okay. So this is actually not enough for computations. Okay. This is still very hard. And to do computation, you have actually to consider a whole space of homotopy automorphisms. And this group of homotopy automorphisms is identified with the group of homotopy components of this space. Okay? I'm not going to explain how I define this space. So what I want to compute is this, and for that, I need to consider this space. Okay? Probably I have no time to explain how I perform the computation. So in case. Okay.
He's going to leave before he explains the computation.
Okay, so yeah. So on this, and you have this group of homotopy classes of homotopy self-equivalences of R, and so the statement that you can identify this group with the path components of a space that you can compute. Okay, now the Grothendieck-Teichmüller groups. At last. Okay, so I will give a very quick definition of a Grothendieck-Teichmüller group. So first, so I can form, so to get something non-trivial, I have to consider some kind of completion in any case. Otherwise, I just get a trivial Grothendieck-Teichmüller. Okay, So in my setting, I will consider Maltsev completion of the parameterized operator groupoids.
That is the same as the pro-unipotent completion.
Yeah, it's the same as the pro-unipotent completion.
Just wanted
Okay.
to-
So the claim, so you have this pro-unipotent completion on groups.
Mhm.
You can extend this completion to groupoids, and it behaves sufficiently well with respect to the monadal structure to give something for opera. So we see that the correction of these groupoids forms an opera, PAB.
Maybe I could just say that if you look at parenthesized break, if you look at chord diagrams, then you want to completely grade it with.
Yeah, you have also, also the chord diagram opera gives
Yeah.
an explicit
Yeah,
model
morphisms, but-
for this Maltsev. You have in that case you have an explicit model, but maybe I will address that next week actually. Okay, so but you have actually a general Maltsev completion
I was just
process.
checking on language, really.
Yeah.
The pro-unipotent completion is the same as
same,
Maltsev.
exactly.
I'm just checking on the language, not the implications of it.
So
Rational unipotent completion or integral unipotent completion?
no, it's a rational. Yeah,
Rational.
yeah, okay, yeah, that's a good point. So so this rational completion combines a pronilpotent completion and a rationalization, a localization. Okay, a rationalization. You localize with respect to all places.
And what happens if you do integral? Can you do integrally?
Yeah, you can do a pronilpotent completion of PAB.
And then what you obtain?
I don't know what you get. Maybe pro-pinilpotent completion would be more sensible. Okay. So, but one difficulty with this Maltsev completion is that it combines a completion and a localization. So this makes things more difficult from our typical viewpoint.
Is it true that the Maltsev completion is the fundamental group of the rationalization of the space?
Yeah, exactly.
The fundamental group of the rationalization of the space is the Maltsev completion of the fundamental group of the original space.
If you start with an nilpotent space,
Okay.
or,
You start with an
this space is not really nilpotent. That's one point.
Here you have to do.
No.
space is not nilpotent.
Okay. It's what you get here is a pronilpotent object. Okay. You get a pronilpotent object.
You mean P hat AB?
PAB art, yeah.
Yeah, but isn't it the? I mean, you take PAB.
Mhm.
That's an nilpotent thing, isn't it?
No, PAB is not nilpotent at all.
Oh, okay.
No, it's break.
Yeah, it's very good. But you have to be careful.
So the automorphisms are the purebred
not
groups.
the-
The pure break.
You have to take the purebred group. If you start by taking the purebred group, and then you take
Okay.
the semi-direct product with the break, with the ordinary break. Otherwise, it doesn't work.
Yeah.
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 And there is no torsion
Yeah.
in the purebred group, so it's not so different from the
Yeah.
nature.
Okay. Okay. Fine.
Okay.
Thank you.
So, and I can also add a unit again. Okay. And so the Grothendieck-Teichmüller group, it's the group of automorphisms of operads in groupoids, okay, which are the identity and object sets, so which fix which are the identity of the. So remember the object sets of PAB are form the magma operad. Okay. Now also considering a group with a 1 upper script, which says that I'm considering a group of automorphisms that fix the braiding toe. Okay. And so I claim that this is equivalent to the other definitions. And the equivalence comes from this combination of a MacLane and of a Joyal straight theorem.
No.
Okay. So because it's just you see so it's a completion. This means you have some kind of conjunction. I mean, every morphism from PAB to PAB hat has a unique extension to the completion. And then this Courant theorem says that to fix such a morphism amounts to fixing the image of the multiplication, so which is the same, the image of the grading, which is fixed again, and the image of the associator. That's why such an ISO at least such a morphism here, amounts to giving a morphism in PAB3, which represent the image of the associator. That way you can, so it's equivalent to some kind of power series in two variables.
Identifying associators
Yeah.
in there, and saying that all you
Yeah.
have to do is
You can
to act on the associator.
Yeah.
I see. I see.
Okay.
I see.
So if you look at, if you go back to this current theorem, that you see that the condition to have such morphisms are equivalent to the classical pentagon and hexagon generations. Okay. That's just a trick with the unit. Okay. So that way you achieve exactly Drinfeld's definition. Actually. Okay. Now let's continue. So I would like to recall that I would like to do topology. So I can take the classifying spaces of this operad in operads to get an operad which is equivalent to D2. Okay. And I take the classifying space of operads of a Maltsev completion of PAB. Okay. Okay. What I get is another operad in topological spaces. And this is in some sense a rationalization of a little two-disk operad. Okay? So rationalization means that you have a chain of morphisms, so morphisms of operads in topological spaces that induce the rationalization of the homotopy groups. So in that case, this is very easy because we have only the fundamental group. So induces the rationalization of homotopy group means that it's the identity of a trivial group in degree different from 1. In degree 1, this is just the Maltsev completion of the pure red groups. Okay? So it could be more difficult to define such realization for more general parts. So maybe that's the kind of thing that I'm going to address next week, actually. Okay, but in fact, so in that case, you can use this Maltsev completion process to get such a model of rationalization. So now what I would like to do is to compute the homotopy automorphisms of this operad. So I have to pick a covariant replacement of this operad. So I pick any covariant replacement of this operad. Okay, that is one. Okay, and maybe I will come back within a couple of minutes the difficulty which creates this construction. Okay. So I start with any automorphism in GT1. Okay. By functoriality, this automorphism induces an automorphism of the classifying space of PAB hat. Okay. And you can lift, so it's some kind of rational homotopy automorphism of D2. Okay. And you can lift this ISO to a self-homotopy equivalence at the level of the covariant replacement, D2 hat. Okay. So you have this covariant replacement. That you need, this covariant resolution, that you need to compute homotopy automorphism groups properly. Okay. And the claims that there is, so we have an ISO here, and you can leave this ISO to homotopy self-equivalence. Okay, so I can conclude with the main statement that this mapping gives a group ISO from GT1Q, so you don't get the whole group of self-homotopy equivalences classes, but some kind of operatic version of a Torelli group. I mean, you get the subgroup of self-homotopy equivalences that are not detected by their action in homology. Okay. So if you start with VGTQ, then you get the whole group of homotopy automorphisms of D2. And the spaces, the homotopy of the spaces.
Is that the same as a component of the group?
Yeah.
Is it the component of things which are homotopic to the identity?
No.
contained in that component. Sorry, no.
No. If you have something which is homotopic to the identity, then it gives the identity in homology.
Yes.
And the statement is that you have more in that case.
More than that,
If you have more, you have GT1 more.
Okay.
Okay? Exactly. Okay. So, yeah. So I should explain maybe just so it's time to, maybe I have 1 minute to conclude. Maybe I just can, so I will not be able to explain so how to compute this, how to prove this statement. So I need to use this group of self-homotopic unities and some kind of Borsfield-Kahn construction to compute this homotopy groups from some deformation complex. Okay. Maybe what I just want to say that in general in topology it's generally considered to be easy to compute the homotopy classes of maps from the classifying space of a group to the classifying space of another one. Maybe if you look at the homotopy automorphisms of the classifying space of a group, okay, it's well known that if G is discrete, then what you get here is the group of outer automorphisms of G. Okay, it's a very simple statement. Okay, so you see this operad D2, it's something which is the classifying space of a discrete groupoid. Okay, so it looks to be something which has this form. Now, if you want to do computation with the homotopicity of operads, you have to perform. I forgot the classifying spaces. You have to perform a cofactor replacement, and this completely breaks this property. I mean, you have some cofactor replacement which have the form of a classifying space of something. Okay, but this something is no longer discrete. Okay, that's the point. At least there is no insight that you have such a cofactor replacement of this object as an operad with G dot discrete. Okay. So that's the main point. Okay. One direction is easy. I mean, the injectivity is easy. You can go back by using the fundamental groupoid picture. Okay. So the point is that to prove that every morphism defined at this level reduces to something which is detected by the action of fundamental groupoids. And that's the claim of this theorem. Okay? So, thank you very much.
In the last transparency, you wrote automorphism of group OP H star D2 there is.
Yeah,
What
the
is
automorphism of this operad.
What is this group?
This is the okay. That's very. I think you get the multiplicative group or something. Yeah, that's exactly GM. Yeah.
GM. I see.
Yeah.
I see.
Yeah. Okay, so
GM?
GM the multiplicative group. Okay, just
So
the multiplication. So the product is fixed by the unit conditions. But it's just something which rescale the Lie bracket. Okay.
So it acts only on this permutation. How to say?
So you see, this is the homology of D2. Okay, I'm looking at the. So it's an operad in the case of grading modulus. It's the Gershnaber operad, and I'm looking at the automorphisms of the Gershnaber operad. Just determine the rescaling of a bracket.
So homology group of D2 of 2 is something like Q.
The homology of
H star of D2 of 2.
2. Yeah, it's
isomorphic to Q.
It's Q in degree 0 and 1. Okay, 0 over 1. But the multiplication has to be fixed by the preservation of units. Okay, otherwise you don't get Q star, you get twice Q star maybe something like that.
So where do you, I mean, are you just using PAB just as a convenience, or is it really essential for the argument?
So it's essential to use PAB, the parenthesal braids, rather than the curl braid operas.
Yeah, but okay, no, but what I was wondering is, could you? I mean, I'm going to ask my favorite question. Why don't you use the Fulton-McPherson opera?
Yeah, I could use the Fulton-McPherson opera.
Because it's cofibrant, right?
Yeah, it's cofibrant. You have to take the rationalization of the Fulton-McPherson opera at some point.
Yes, you'd have to. So could you just run the argument with the rationalization of the Fulton-McPherson opera?
Yeah, in fact, so I don't really need. So I need this PAB to detect the automorphism at the level of some fundamental group values.
And then you'd say that is
That's the main point.
you'd say what you'd say is that that's the fundamental group point of the Fulton-McPherson
Yeah, exactly.
opera.
Yeah,
You would
exactly.
detect things by using
Yeah, I
fundamental
could
group
use
point.
that. I could use
Yeah,
the
okay,
PAB.
that's fine.
Yeah,
That's
it's another picture actually. It's, yeah, I could do this one. So this one is cofibrant with respect to the model structure which I'm using. If you look at the composition with unit operations,
Yeah.
so it's that you have to perform
But to perform some
rationalization.
calculation,
I don't.
you have to use fundamental group points to perform some calculations.
Yeah.
Yeah.
And but actually, to perform the computation, so
But
Yeah.
that all makes sense.
yeah.
Yeah.
On the left hand side, you can put the preferred part, but actually, I'm taking the cut-ripple resolution.
But it all makes sense because in second,
Yeah.
I mean, what you're saying, passing the fundamental group points, what you're saying is these FM spaces.
Maybe, yeah.
Okay, by
On
one.
the left hand side, you don't need to take the completion. So maybe you can put Fulton-McPherson on this side
Yeah.
and take. So here you can compute. You could perfectly compute. So you check that this. You have such an ISO. From the Fulton-McPherson opera to maybe on the right hand side you can take this completion. You don't have to perform rationalization on the left hand side. What you need is to consider a subpart which consists of maps that induces an ISO at the level of rational homotopy groups. So you have such an identity. So now the exercise is to try to construct the image of an element in GTQ in this morphism set.
Yeah.
So in the right hand side of your theorem, can you replace it D2 by D3, D4, and then make sense?
Yeah,
Right hand side.
yeah, but I don't know what is on the left hand side.
Yeah, left hand side is
That's the point.
right hand side is
Yeah.
makes sense.
Yeah, it makes sense. So maybe that's what I'm going to explain. So it makes sense. So the point is that you have to define a rationalization of D3 and D4 without the fundamental group picture.
Yeah. I mean,
Yeah.
but
Yeah. This is the kind of.
I mean D3. I mean, it's simply connected, right?
Yeah, D3 is simply connected.
Yeah.
Yeah, D3 is simply
So
connected.
there's no fundamental group around.
Yeah.
So you mean nothing interesting or?
No. I feel it would be extremely interesting. It's I don't know how to do this computation for the moment. So. So it's very serious. This is to find a replacement.
But it's
very
a
serious to
different phenomenon.
Yeah.
It's not dominated by the fundamental group. It's a different phenomenon.
Yeah.
It's something to do with the other homology groups or homotopy groups.
I'm not so sure it's a different thing.
Well, at least, yeah.
So the point that is to find a replacement of a fundamental groupoid in the D3 case.
Yeah. Okay.
Something which is simpler than the operaid itself, but which is sufficient to detect the self-homotopic
Yeah.
frequencies.
Yeah. Okay. Yeah. So,
That's the main point.
Yeah.
Okay, so thank you very much. So next week I'm going to do some rational homotopy theory. So first some recollections about Sullivan's theory,
Yeah.
and then I will explain how to extend Sullivan's theory to operads, and how to define rationalization for more general operads. Okay, thank you very much.
Thank you.